Hi, so we're moving on to chapter 4 right now, and this is where we start to get into the actual meat of statistics. We've laid down a bunch of background work with, the study of uh, variables and parameters of data, with uh, random variables and probabilities, and specific families of random variables, the normal variable and the binomial variable. And so it is with all of these tools that we build up the theory of statistics. I remember the end game out of all of this is if I go out into the world and I gather up a bunch of data and I look at it, I want to be able to know whether or not I could say something about that data and what exactly that data tells me. And so we've laid all this foundation to get to being able to do those things. So the last sort of piece of theoretical information that we need to be able to accomplish this is the central limit theorem, which is going to be the focus of this video. So if you're following along the text, I'm kind of doing things a little bit out of order from the text. They mention the central limit theorem in 4.1, but they don't go into a lot of details about it in 4.4, and I'm going to go into some more of that detail here. So, um, we in order to make sense of what the central limit theorem tells us, we have to go back to chapter 2. So let's say x um, is a random variable with mean or expected value mu and standard deviation sigma. Let x2 be x plus x over 2. What is e of x2? And what is the variance of x2? All right, so those are going to be the questions that we're asking ourselves for now. So let's take a step back and take a gander at what's written here. So x is a random variable with mean mu and standard deviation sigma, and x2 is the mean, right, of x with itself. So you imagine, for example, if x is rolling a dice and the outcome of that die roll, what x2 is summing two die rolls and taking their average. Right? And so we want to know what the average value or what the average value of x2 is, say, and what the variance of x2 is. And so if I work this out or algebraically using what we covered in chapter 2, what I know about the expectation of x2, it's that it's the expectation of 1/2 of x plus x. Which is 1/2 the expectation of x plus x, which is 1/2 the expectation of x plus the expectation of x, which is just the expectation of x, which is just mu, right? So if I work all that out, let's take a think about what this means. So x2 is 1/2 of x plus x, right? That's how it's defined. And I could pull the 1/2 out by the properties of expectation that we discussed in chapter 2. And then I could split apart the expectation of x plus x into e of x plus e of x, because that's also one of the properties. Oh, I think I forgot to close a parenthesis here. Yoink. Right? And then this is 2 e of x's times 1/2 gives me 1 e of x. And e of the expectation of x is mu because we said that the mean was mu, right? So what that's telling us is that the average value of averaging 2 of x's is the same as the average value of x. And to some extent, that's obvious, right? Like if I roll 2 die, or if I roll 1 die, the average outcome is 3.5. If I roll 2 die and take the average, we wouldn't expect that to change. Like, why would it go up or down, right? It should still be 3.5. Okay, so it's not. I don't want to put up a new slide, so I'm going to erase all of this, and we're going to now compute the variance. And so I'm going to go ahead and get rid of all of this. We're going to note that e of x2 is mu, and then let's talk variance. So when looking at the variance, what color do I want? That looks okay. So when looking at the variance, just like with the expectation, I'm talking about the expectation of 1/2 of x plus x, right? Right? No biggie here. But what's different now is that when I pull the 1/2, out, remember that when I pull the 1/2 out, excuse me, when I pull the 1/2 out of the variance function, I don't get 1/2, I get 1/2 squared. Right? Do you remember that whole thing? And so I get 1/4 times the variance of x plus the variance of x. And this gives me 1/2 times the variance of x, which is sigma squared over 2, right? If the standard deviation is sigma, then the variance of x is sigma squared. And so the variance of x squared is sigma squared over 2. And then it's worth noting then, just as an aside, that the standard deviation of x2 is the square root of sigma squared over 2, which is just sigma over the square root of 2. All right? And so what we noticed is that, all right, if my original variable has mean mu and standard deviation sigma, my new variable still has mean mu, but it now has standard deviation sigma over square root of 2. Square root of 2 is about 1.4 something, and so what we get is a number that's less than sigma, right? And I worked all of this out in detail so that we can move on to the general case, which is, all right, that x be a random variable with mean mu standard deviation sigma. Let's say xn, I need a little bit more room than that. The average of n copies of x. And we want to ask ourselves the same questions we asked ourselves when there was just 2. So here, basically, n is 2, and now we just want to examine the general case when n is n. Well, the expected value of xn is going to be computed the same way. It's the expected value of x plus dot 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 x over n, which is 1 over n times n copies of e to the x, which is mu. Right? It's the exact same computation as before, right? I can pull out a 1 over n. There's n copies of e to the x, so I have n e to the x here, and I get mu. The variance of xn is going to be the variance of the whole thing again, which is going to be 1 over n squared, right? When I pull out the 1 over n, it becomes n squared times n copies of the variance of x, which is going to be, well, an n here and an n there cancel, so sigma squared over n. And so the standard deviation of x to the n is going to be the square root of the sigma squared over n, which is sigma over square root of n. So your parameters are mean mu and standard deviation sigma over square root of n. All right. And so what this is telling us is that if I take more and more samples and I take the averages of the sample, that the outcome of those averages, that the average outcome of those averages remains the same as the original average outcome, but that the variation or the standard deviation of those outcomes gets less and less as n gets bigger and bigger, right? As n gets larger, square root of n gets larger, and sigma over square root of n gets smaller and smaller and smaller, right? And if you think about this, this is kind of common sense, right? This is exactly why when we, if you want to know if a coin's like good, if a coin, let's say, is weighted fairly, you don't just flip it once and then see if it comes up heads or tails, because that doesn't tell you anything, right? Even if it flips 10 times, it doesn't tell you much. You have to flip it, hundreds, maybe thousands of times. And once you record all those results, right, the variation in the proportion of coin flips that are heads or tails, that gets smaller and smaller, and the average number of coin flips should still be 1/2, right? So, I'm going to go ahead and erase this bottom part here, because I actually want to continue on with this, because the statement of the central limit theorem has all of this as hypothesis. So let's consider this a brand new slide. So we still have x as a random variable with mean, mu, standard deviation, sigma, and we're still going to let xn be the average of a bunch of x's, n of them to be precise. What the central limit theorem states. The central limit theorem. As n gets sufficiently large, xn may be approximated by n mu sigma over square root of n. So this really is, in a sense, a fundamental theorem of statistics. And what it's telling us is that, all right, for variables that have a mean and a standard deviation, as you make your n sufficiently large, not only will the mean and standard deviation of the averages of those variables get to be closer and closer to mu and sigma over square root of n, that the distribution of the averages of those variables approaches normality, right? And so you might remember in the normal curve videos, I asked, of all of the possible probability distributions, why don't we focus on the normal distribution so much? And one of them was that the normal distribution is a commonly occurring distribution in nature. Correct. But there's another important reason, which is that given most other distributions, any distribution that yields a mean and standard deviation, that repeated sampling of those distributions gets you a normal distribution as long as your sample is large enough. And this is, let me write that out explicitly. This is super important here. For any x with a mean st dev, repeated sampling of x and averaging gives us normality. This is a big deal, and to sort of demonstrate that, let's go ahead and I don't know. Let's consider ourselves a question here. Um, how many phone calls or maybe what is the probability that a police station receives over 20 calls a day? Well, I have no idea, right? And based on this, you can go ahead and and try to guess, but we have no information whatsoever, right? And more importantly, we don't even know what the probability distribution of this thing looks like, right? If we knew it was some sort of binomial distribution and we had the n and the p, we could figure that out, right? We could count 20 and above. If we knew it was a normal distribution and we knew the mean and standard deviation, we can go ahead and figure that out. But even if you knew the mean and standard deviation, if you don't know the shape of the distribution, you have no idea how to answer this question. So the probability type of cause per day, who knows, right? We have no idea what that distribution is. But what if we said on average over 100 days, over 20 calls per day? Aha! If we take the average over sufficient n, in this case n is 100, usually the rule of thumb is that 30 or more is sufficient to make an approximation normality. You want to check the specifics to make sure, in practice, the best practices of your specific discipline to see when it is okay to make the assumption that things are normal. But assuming we can make this assumption, then at n equals 100 days, this variable is a normal variable. And so all I need to do is get an estimate for the mean and the standard deviation, and I can go ahead and try to do this computation, right? And so the nice thing about that is I never need to know what this question mark is. It's really not important, right? That once I have a sufficiently large n to force things to be normal, that's good enough to make my approximation. So we might remember this from when I talked about binomial variables. But let's not talk about a binomial variable. We said in the previous video that binomial variables, as n gets large enough, uh, become normal, and that's true. But what's also true is that all probability distributions that have a mean and standard deviation as it takes sufficiently large sample sizes can be approximated by a normal distribution. All right, so what we have here then is a probability distribution which has a 0 chance of giving you 0, a 1/6 chance of giving you 1, 1/6 chance of giving you 2, 1/6 chance of 3, 4, 5, 6. So it's rolling a dice, basically. And for now, I'm going to set n back equal to 1. And if I go ahead and I run that, then right, it rolls the dice 1,000 times. Boom, boom, boom. It's pretty even, right? I can do it again. And it's not exactly the same distribution, but they're all still pretty even. And there we go again. And no surprises here, right? If you roll a dice 1,000 times, you don't expect maybe exactly the same number of the 6 outcomes. It's not actually possible because 1,000 is not a multiple of 6, but expect it to be pretty close, right? Okay. So what if I sum 2? Or I roll a dice and I took their sum, then, right, and we've seen this from chapter 2, right? 2 is the smallest your sum can be, and that's pretty rare because you need to roll a 1 on both dice. 12 is also pretty rare because you need to roll a 6 on both dice. 7 is the most common because you can roll 1 and a 6 or 2 and a 5, 3, 4, 4, 3, 5, 2, 6, 1, right? So it occurs the most often. And if I roll this again, it's not going to deviate too much, right, from that outcome. Okay. And then if you imagine what the average of 2 dice rolls is, I just take my sum and divide it by 2, right? Now that's my average. If I bump up to 3, all right, there's a little outlier event here, but for the most part, I get a nice little curve. And it's already kind of starting to look normal here, right? At this point. But there's enough of these bumps around here that sort of suggest not normalcy. So let me bump it up to 30. That's looking pretty good. And let's bump it up to 100. That's what we were doing with the police station example. And so we should notice two things, not just the general normality of the shape, but that before our outcomes basically took up the entire width of this display, and now it's just this tiny little piece here, and that's a result of the sigma over the square root of n component. What's going on is that as we bump n up, our outcomes get less and less variable and approach the mean more and more and more. And so if I were to bump up, let's say to 500, our results will be further concentrated. 500 is a lot, so it's going to take it a second. Right? It further and further concentrates everything to this middle here. Right? And let's go back and compare that to 2 again, right? Where things were really spread out. And so those are the two features of the central limit theorem. As n gets bigger, the results get more accurate, and the results approach a normal distribution, which will allow us to make predictions about the random variable, right? Because we know from chapter 3, or at least the first half of chapter 3, how to compute all sorts of stuff about the normal curve. So if you have some random variable with some weirdo distribution, you just need to sample it enough times so that it's normal, and then you can know things about it. All right, and just to give us another example, let's give one that has a very skewed distribution. 10% chance of 0, 20% chance of 1, 30% chance of 2, 40% chance of 3. And let's pop that back down to 1. Run that, all right? Between 100 and, I want to say 375 here, we get like a nice little curve. 3 is more likely than 0, which that's what we said, right? If I sum together 2 of these, all right, we can already see the dip off here, and that's because in order to get a 6, you have to get a 3 twice. And that's still less likely than getting a 4, which you can add up in a bunch of different ways. Bump up to 3, right? And we can start to see, right, as I bump up the number of sums, that this thing is starting to look pretty, it's more and more normal per step, right? Let me do 4. All right, it's still not normal. It's still, tailed off here and not quite symmetric, but it gets more normal as I take more and more sums. So let's bump up to 30. Aha. That's starting to look pretty normal, right? 50. All right, and again, the other thing we observe, of course, is that the width, the relative width, right, of our distribution gets smaller and smaller. 100. And now, the only difference between this and the die rule was that the mean is shifted over some, right? It's basically still getting narrower. It's basically still looking normal. 500. All right, and now it's essentially indistinguishable, right, from what we were doing before. All right. So maybe one last kind of thing to talk about um, would be something like a practical, maybe application of this before we get into the meat and potatoes of statistics in upcoming videos. So let's just say, hmm, the cause to a police station are distributed with mu equals, let's say, 18, sigma equals 5. What is the probability? Let's say per day. Cause per day. What is the prob that over, let's say, 30 days, they get over 20 calls per day on average? So, let me tell you right off the bat, the probability is going to be really small. All right, and the reason it's going to be really small is because, well, the mean, on average, this station only gets 18 calls per day, right? Uh, I don't know the shape of the distribution, so I have no idea uh, uh, how to compute for one day the probability that they get over 20 calls. It's not normal, right? It's definitely not normal because, well, uh, a what am I trying to say? A normal curve is continuous, and calls to police station are definitely not continuous, right? Like I can't get 18 and a half calls a day, but it can be approximated with a normal curve if I make my n here large enough. But let's talk about what that means still. How do I know this outcome is going to be small? Well, you're getting over the mean number of calls on average for 30 days. And that's a lot. That's not going to be a very common occurrence, right? And so we should not expect a big probability here. But what we know is that x30 is approximately n 18 5 over square root of 30, right? And I'm talking about over 20 calls a day. So we go over to Desmos, and yep, and we go over to our normal curve. We're talking about a curve whose mean is 18 and whose standard deviation is 5 over the square root of 30. And we want to know the probability that you get more than 20 calls on average. So let's say, oh, between 20 and a million calls. Right, so there's our 20 right there. And so our probability then is about, we pull that back up, 0.1, or sorry, 0.01423. All right. In the next video, we are going to talk about confidence intervals.